Hello, welcome to another module in this massive open online course on estimation for wireless communication systems. So, we are looking at a different estimation scheme or a different channel estimation scheme for orthogonal frequency division multiplexing, that is OFDM systems, and we call this the comb type pilot based estimation, right. So, we are looking at a comb or basically CTP. This is your comb type pilot for OFDM or orthogonal frequency division multiplexing, alright. And we said again, just to refresh your memory, we are going to consider a system with n equal to 4 subcarriers and L equal to 2 tap ISI channel L equal to 2 tap ISI channel. And what we did in the previous module was we looked at the 4 symbols loaded onto the n equal to 4 subcarriers, that is x0, x1, x2, x3, okay. And we said we are not going to load all the subcarriers with pilot symbols, rather we are going to load only 2 symbols, that is corresponding to subcarriers L equal to 1, 3. These are pilot symbols, and in fact we said these are the corresponding L equal to 1 to 3, these are your pilot subcarriers, okay. And similarly we have x0 and x2, the rest of the subcarriers, that is subcarriers L equal to 0, 2, these are your information subcarriers. These are loaded with the regular information symbols, that is the transmitted information over the channel. So, these are loaded with your regular information symbols. And now, what we do is now we have basically what we have is we have 2 pilot subcarriers, that is capital X1, capital X3. These are the 2 pilot symbols and the information symbols, that is capital X0, capital X2. Now, we have basically what we have is basically the pilot symbols are sort of meshed with the information symbols, therefore, this is known as a comb type pilot arrangement, that is what we saw yesterday. And now, once we have this block of symbols, that is pilot symbols and information symbols that are loaded onto the subcarriers, we take the n point, that is n equal to 4 point IFFT to generate the time domain samples, okay. That is similar to the regular OFDM. So, now what we do is we do your n equal to 4 point IFFT to generate the samples. This are your x0, x1, x2, x3, okay, which are the time domain samples. These are the time domain samples, and in fact, it is these are given as the kth sample is xk equals 1 over n summation L equal to 0 to n minus 1 capital XL e power j 2 pi KL divided by n. Now, once you generate the time domain samples, we add the cyclic prefix, that is basically where you have x3, that is some symbols from the tail prefixed in the beginning. So, you have now x3, x0, x1, x2, x3, and these are transmitted basically over the transmitted over the L equal to 2 tap ISI channel alright. These are transmitted over the L equal to 2 tap ISI channel, which is your yk equals H0 xk plus H1 xk minus 1 plus Vk, all right. So, once you transmit this cyclic prefix, basically once you transmit the time domain samples with the cyclic prefix over this intersymbol interference channel, now what happens? Basically the channel, the action of the channel over the samples is that of circular convolution. Therefore, what you have is the received output y is h, which is circularly convolved with x plus v. Okay. Now, once you take the FFT, you take the FFT of the output samples y, okay. This circular convolution becomes multiplication in the FFT or the frequency domain. Yeah, because in the frequency domain becomes multiplication in the frequency domain. Therefore, across subcarrier L you have YL equals HL times XL plus VL. Yeah. So, this is basically across the, this is basically across subcarrier, this is across subcarrier L in the frequency domain, all right. So, this is something that you have to remember, that is this is in the FFT or the frequency domain, that is you take the FFT of the received output samples, all right, because the channel is circularly convolved with the time domain samples. Therefore, in the frequency domain the corresponding channel coefficients are basically multiplied by the corresponding FFT coefficients of the samples, but the FFT coefficients, but the samples remember are generated by the IFFT of the symbols loaded on the subcarriers. Therefore, the FFT of the samples is nothing but the symbols loaded on the subcarriers. Therefore, the output YL of the Lth subcarrier is the channel coefficient HL times capital XL, which is the symbol loaded on the Lth subcarrier, plus the noise, which is the noise on the Lth subcarrier, that is given by the Lth FFT point of the time domain noise samples. Okay. So, we can look at this, this is the channel coefficient on the Lth subcarrier, and this is the symbol loaded onto the Lth subcarrier. Okay. Now, specifically for channel estimation, remember we are interested in the pilot symbols or the pilot subcarriers. Therefore, we have to extract the output symbols corresponding to these pilot subcarriers, and remember these pilot subcarriers correspond to small l equal to 1 and small l equal to 3. These are our pilot subcarriers. Okay. So, our pilot subcarriers are these are basically our pilot subcarriers. Therefore, now what we are going to do, we are going to extract the output symbols corresponding to the pilot subcarriers, that is y1 equals h1 x1 plus v1, y3 equals h3 x3 plus v3. all right. Since L equal to 1 and L equal to 3 are basically the pilot subcarriers, therefore, we are extracting the output symbols Y1 and Y3 corresponding to these pilot subcarriers. Okay. So, these are the outputs corresponding to the pilot subcarriers. These can be used for channel estimation, right. These are the outputs corresponding to your okay. Now, writing it in matrix form, I have again I can write it again similar to what we did previously for OFDM. I can write it in matrix form. This is Y1, Y3 equals X1, X3 times H1, H3 plus your noise vector V1, V3, and now therefore, what you have is basically you have, let us call this output vector Y check, let us call this diagonal matrix of pilot symbols as X check. This is in fact the pilot matrix. Let us call this vector as your H check plus this is V check. So, basically Y check, what is this? This is your 2 cross 1 vector, this is also a 2 cross 1 vector, basically an L cross 1 vector. This is, I am sorry, this is a 2 cross 2 matrix, this is a 2 cross 1 vector and this is a 2 cross 1 vector. And observe again that this X check, this is the diagonal matrix of pilot symbols this is the diagonal matrix of pilot symbols x1 and x3, that is the diagonal elements are the transmitted pilot symbols x1 and x3, all right. So, therefore, it is a diagonal matrix and in fact, this is also the pilot matrix for this comb type pilot based OFDM channel estimation scheme. Okay. So, this is basically our pilot matrix. Okay. So, this is our this is our 2 cross 2 pilot matrix. And now, obviously, therefore, our system model, what is our equivalent system model? Our equivalent system model is Y check. We have this Y check equals X check times H check plus V check. Therefore, the least squares problem for channel estimation can be formulated as the least squares problem for channel estimation can now be formulated as norm y minus x or norm y check minus x check whole square. This is the same, this is your, and one has to find the H check, which is the, which minimizes this least squares cost function, all right. So, we have to find this vector H check, right, and that is found as from the least squares minimization problem, that is the H check which minimizes this least squares cost function, that is norm of Y check minus X check times X check norm whole square. Okay. And we know the solution for this least squares cost function, again similar to what we have done previously in the case of OFDM. I have the estimate H hat equals X check Hermitian X check, that is a pseudo inverse of X check times, in fact X check Hermitian times Y. However, now this is a diagonal matrix and invertible. X check is a diagonal matrix, implies X check is invertible. Therefore, specifically for this scenario, I mean although it is not generally valid, I can write this as, since X check is an invertible matrix, X check Hermitian. So, this becomes X check inverse, X check Hermitian inverse times X check Hermitian times Y check, X check Hermitian inverse times X check Hermitian, this is identity. So, this basically becomes your X check Hermitian. So, your H hat basically is your, in fact, this X check inverse times Y. So, that is the estimate of the channel coefficient. In fact, now this can be implemented rather very easily, because X check is a diagonal matrix. So, the inverse of the diagonal matrix is nothing but the another diagonal matrix with the reciprocals of the diagonal elements. Therefore, what we have is basically your, in fact, H hat 1, that is the estimates of the subcarriers, estimates of the channel coefficients of the pilot subcarriers are basically your inverse of this diagonal matrix times Y1, Y3 outputs on the pilot subcarriers plus the noise V1, V3 on the pilot subcarriers, and therefore, now you can see this is nothing but inverse of the elements, reciprocals of the elements on the diagonal, because it is a diagonal, as we said X check is a diagonal matrix. So, its inverse is nothing but another diagonal matrix with the reciprocals of the diagonal elements, which implies finally, if you look at this element by element, therefore, the estimates are H1, again you can see this is x 1 over x 1 times y 1, H hat 3 is 1 over x 3 times y 3. I am sorry, there should not be, there is no noise in the estimate. So, this is basically this part, and therefore, what we have over here is H hat 1 equals y 1 divided by x 1, H hat 3 equals y 3 divided by x 3. So, these are basically, what are these? These are the estimates of the channel coefficients on the pilot subcarriers. These are the estimates of channel coefficients H hat 1 comma H hat 3 corresponding to the pilot subcarrier, and that is something important to realize. That is, whereas previously when we load pilot symbols onto all the subcarriers, we have the estimates of all the channel coefficients corresponding to all the subcarriers. However, now we do not have the estimates of the channel coefficients corresponding to all the subcarriers, we can estimate only those channel coefficients corresponding to the pilot subcarriers, and from these estimates of the channel coefficients on the pilot subcarriers, we are going to see that interestingly we can recover the estimates of the channel coefficients on the rest of the subcarriers, and the trick to do that lies in realizing the following. Now, if you go back and look at these channel coefficients in the previous module, now what you can see is basically the channel coefficients on the subcarriers can be expressed as basically the channel coefficients on the coefficients, the channel taps, alright. So, I have H1 which can basically be expressed as H0 minus JH1, and I have H3 which can be expressed as H0 plus JH1. Therefore, now what you have is, if you go back So therefore, now what you can see is the following thing. Therefore, I have H1 equals H0 minus, let me write it correctly, H0 minus JH1 and H3 equals H0 plus JH1. Yeah. So, these are the coefficients on subcarriers, and H0 and H1, remember these are the channel taps in the time domain. These are the channel taps in the time domain. In fact, the channel coefficients are basically, if you remember, the channel coefficients are basically derived by the 0 padded FFT of the channel tap. So, I have H0 H1, I look at the n equal to 4 point FFT or the fast Fourier transform, or H2 and H3, and this is basically your n equal to 4 point FFT. So, the channel coefficients in the across the subcarriers, the channel coefficients in the frequency domain are basically given by the FFT of the channel taps, in fact the 0 padded FFT of the channel taps in the time domain, alright. So, now if you look at this, I have H1, capital H1, that is the channel coefficient across subcarrier 1, equals H0 minus JH1, and capital H3, that is the coefficient across subcarrier 3, equals H0 plus JH1. Now, I can write this in a matrix form, and that will become, interestingly, that will become H1 H3 equals, we have 1 minus J, 1 J into the channel tap vector H0 H1. And now, if you look at this, therefore, now if you look at this, it is easy to see that the channel taps in the time domain, that is H hat 0 H0 H0 H1 is the inverse of this matrix, this transformation matrix 1 minus J 1 J, the inverse of this times H1 H3, and in fact, the only difference is basically we have the estimates of the channel coefficients H1 H3, therefore, I have the estimates that correspondingly, therefore, if you have estimates on the right, you will have estimates on the left. So, basically I have the estimates of the channel coefficients H hat 1, H hat 3 on subcarriers 1 and 3. From this, I can, from these estimates, I can basically recover the estimates of the channel taps, the small h hat 0 and the small h hat 1. In fact, that is basically, that holds the key to this entire process, because remember when we started, we said that there are only two unknowns in this system, and these two unknowns are in fact the channel, the channel taps, the time domain channel taps, that is your small h0 and small h1. So, basically I need two equations to determine these time domain channel taps, and those two equations are given by my capital H1, that is the subcarrier coefficient or estimate of the subcarrier coefficient on subcarrier 1, and capital H3, that is our capital H hat 3, that is the estimate of the channel coefficient on subcarrier 3. And from this now, therefore, I can find the estimates of the time domain channel taps, and of course, this 2 cross 2 matrix is easy to invert, that is 1 over the determinant, that is 1 over 2j times interchange the diagonal entries, that is j and 1, and well the negative of the off diagonal entries. Okay. So, interchange the diagonal entries and the negative of the off diagonal entries, that is j comma minus 1, and that is basically equal to now h hat 1 H hat 3, and that basically gives me my H hat 0, H hat 1. These are the estimates of basically what are these? These are the estimates of the time domain channel taps, and that is interesting. So, you can use this linear transformation to get estimates of the time domain. These are the estimates of the time domain channel taps, and that is what we have. And therefore, now you can see that H hat 0, this basically implies that, now writing it out, I have H hat 0 equals 1 over 2 j times, well, j times H hat 1 plus j times H hat 3, and similarly H hat similarly H hat 1 is equal to 1 over 2 j minus H hat 1 plus H hat 3. Okay. So, these are the estimates of the, and remember we already said these are basically your estimates of the channel taps in the time domain. Now, from the estimates of the channel taps in the time domain, so basically these are given as small h hat 0 equals 1 over 2 j times j times capital H hat 1 plus j times capital H hat 3, small h hat 1 equals 1 over 2 j times minus capital H hat 1 plus capital H hat 3. So, these are obviously capital H hat 1 and capital H hat 3 are the estimates of the channel coefficients across the pilot subcarriers in the frequency domain. And now, basically from these the rest of the subcarrier coefficients can now be calculated. So, now I can use the estimates of these channel taps small h hat 0 and small h hat 1 in the time domain and compute the estimates of the rest of the subcarrier coefficients, and that can be done also as follows. Now, again we go back to where we expressed the subcarrier channel coefficients in terms of the channel taps and see how we can use that once again, and that is basically done as follows. Now, if you look at this again, I have H0 basically you can see equals small h 0 plus small h 1, all right, and the coefficient across subcarrier 2 is small h 0 minus small h 1. Okay. So, now I can go back again and I can use this property. So, basically what I have is, interestingly what I have is I have capital H 0 equals small h 0 plus small h 1, capital H 2 equals small h 0 minus small h 1, and now I can basically do these estimates as capital H 2 H hat 2 equals. So, basically now you can see the estimates capital H hat 0, capital H hat 2, these are estimates of your channel coefficients for subcarriers L equal to 1, 2, or which are basically the estimates of the channel coefficients for the non-pilot subcarriers or estimates of channel coefficients for the information subcarriers. These are basically your these are the estimates of the channel coefficients basically for the information subcarriers, and that is what we have over here. So, if you look at this, we have something very interesting. So, now that completes it basically. Now, if you look at it, that basically completes the problem. Now, we have the estimates of the channel coefficients on all the subcarriers basically H hat 1, capital H hat 1 and capital H hat 3 we estimated from the pilot subcarriers, alright, from the pilot symbols transmitted on the pilot subcarriers. From these we estimated the channel taps, and from the channel taps we estimated the rest of the channel coefficients corresponding to the non-pilot subcarriers, alright. And so that is very interesting. So even though you are transmitting only 2 pilot symbols on 2 subcarriers, that is you are not transmitting pilot symbols on all the subcarriers, you are only transmitting a few pilot symbols on a few pilot subcarriers, you are able to basically extract the estimates of the channel coefficients on all the subcarriers. So basically let us note that down, that is, although one is transmitting L equal to 2 pilot symbols, one is able to obtain the estimates of channel coefficients on all the subcarriers. And therefore, what is the advantage of this scheme? What is the advantage of this comb type pilot scheme? Again, that is obvious, something that we have already said at the beginning, that is we are only transmitting pilot symbols on a few subcarriers. Therefore, the rest of the subcarriers can be used to transmit the information or the data symbols, and that significantly increases the bandwidth efficiency, alright. So let us note that down also, that is what is the advantage of your comb type pilot based channel estimation scheme. What is the advantage of comb type pilot based channel estimation scheme? And that is something that we already seen. Just to repeat it one last time, that is I have x0, x1, x2, x3, x0, x1 and x3, these are your pilots or your pilot symbols, x0, x2, these are your information symbols, these are the information symbols, so since you are transmitting pilot symbols and information symbols, that is you are not entirely transmitting pilot symbols. So since the pilots are loaded on fewer subcarriers, in the comb type pilot transmission, pilot symbols are loaded onto fewer subcarriers, and the rest are loaded with rest of the subcarriers are loaded with information rest of the subcarriers are loaded with information symbol. Therefore, this improves the bandwidth efficiency. Therefore, information rate and this improves the bandwidth efficiency. That is something also interesting to note. This improves the bandwidth efficiency . this significantly improves the bandwidth efficiency of the system. Alright, so that is what we have seen. So that is basically in summary the comb type pilot based channel estimation scheme for OFDM. What is interesting about this in comparison to the previous conventional pilot based OFDM channel estimation scheme is basically you are loading pilot symbols only onto a fewer subcarriers. Therefore, the rest of the subcarriers can be used to transmit information symbols, alright. And the channel estimation proceeds by first estimating the channel coefficients in the frequency domain across the pilot subcarriers, convert them back to the estimates of the channel taps in the time domain, and from the estimates of the channel taps in the time domain estimate the rest of the channel coefficients corresponding to the rest of the subcarriers, that is the non pilot subcarriers or the information symbol subcarriers. And therefore, now even though you are transmitting a fewer pilot symbols, you are basically able to establish the channel coefficients corresponding to all the subcarriers. That in summary basically captures the spirit and also basically the method of this comb type or CTP based channel estimation for an orthogonal frequency division multiplexing OFDM system. Alright. So, we will stop this module here, and in subsequent module we will look at an example to illustrate this further. Thank you. Thanks very much.